Today we're talking about radioactivity and nuclear decay and the fundamental building blocks of the universe, which are atoms. This is our most chemistry focused part of physics, but I think you'll see the physics in. So let's start with what is an atom? An atom is the fundamental particle making up the universe, or at least that's what we used to think before we discovered quarks and all the other tiny, tiny, tiny particles that make up the universe. But still, our fundamental building block in many ways is the atom, because atoms are what are chained together to make molecules, and the molecules are what give the things around us the features that they have and the properties that they have. So you can see an atom is a tiny, 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 tiny thing. So what is in the atom? The atom has two main parts, the nucleus and the electron cloud. In the nucleus, there are protons, which have a positive charge, and neutrons, which have a neutral charge. These make up 99.99999% of the mass in the atom, but only 0.00001% of the volume of the atom. So they're very small, but they have almost all the mass in the atom. Electrons are in the electron cloud, which surrounds the nucleus. It makes up 99.999% of the space, but has 0.00001% of the mass. Electrons have a negative charge and are stored in different orbitals. If you look at a periodic table, you can see how mankind has organized our knowledge about the elements. Each cell on the periodic table contains the atomic symbol for the element, as well as the name, and two numbers. In the upper left, or often at the bottom of a cell, you'll see the atomic number. The atomic number is the number of protons in the element. That's what defines the element. In the upper right, or often at the top of the box, you see the atomic mass. That is the number of protons plus number of neutrons. And again, that makes up almost the entire mass of the atom. Now notice that it's not a round number, 63.55 or 127.60. That's because these masses are averages. Let's take a look at the four forces that make up our universe. First and most strongest, we have the strong nuclear force. The strong nuclear force is what holds protons and neutrons together in the nucleus of the atom. After that comes the electromagnetic force. That's the force that attracts positively and negatively charged things, and that's what keeps the electron cloud close to the nucleus. Third, we have the weak nuclear force, which in a way kind of holds the neutrons together. And finally, this weakest force in the universe is gravity. However, we notice gravity all the time, right? Even though it's the weakest force. That's because gravity works over such an incredibly long distance. There are at least two forces acting on protons when they're in the nucleus. We have that strong force, which is holding them together. This strong force only works at a very short range though. So the protons and neutrons that are very close to each other, they are held together by the strong force. The electrical force though makes those protons want to push apart. But because they are close enough together, the strong force overwhelms that electrical force and the nucleus does not break apart. The electrical force is a longer range force though, and that means that the electrical force or electromagnetic force can still act on the electrons in the atom and prevents them from escaping the atom most of the time.
What's going on? Why aren't you seizing the boy?
So, why can't the strong force hold large atoms together? That's because it only acts over a short distance, a very short distance. Like this Tyrannosaurus, it has a very strong ability, but can only act over a very short distance. So in every atom, we have these two forces competing against one another. The electromagnetic force, which is trying to break the nucleus apart, and the strong force, which is holding it together. The larger an atom's nucleus gets, the more unstable it tends to be. Neutrons, in the right proportion, can help balance this out by putting the protons a little bit further apart, decreasing the amount of electromagnetic repulsion. Yet they still have that strong nuclear force that acts between those protons and neutrons. Now, if you put in too many neutrons, the element once again gets unstable. So it's this balance between the number of protons and number of neutrons in an atom. Once you get to an atom of a set size, specifically uranium, 92 atomic number, every element is radioactive because they are all unstable because they are just so large. So what makes an atom stable versus unstable? Well, it's a balance between the number of neutrons and number of protons in an atom. It's not a perfect one-to-one ratio, but it is a balance between those two. If the atom has an atomic number of less than 92, then it won't undergo alpha decay. And if it has an atomic number of less than 83, it won't undergo other forms of decay if it has a stable balance between the number of protons and neutrons. Unstable atoms tend to have very large nuclei or have an untenable balance between the number of protons and number of neutrons, as we saw in the earlier video. Here we have a periodic table, and again in the cells you can see the atomic number in the upper left and the atomic mass in the upper right. This one also has a table of radioactive isotopes, and you can't really see on here, but in that table there are many isotopes of these elements that are radioactive, meaning that they undergo decay. So what is an isotope? An isotope is a element that has a different number of neutrons. That means it has the exact same atomic number, the same number of protons, but a different number of neutrons. Many of these isotopes are unstable and thus radioactive, meaning they emit particles. Here we have atomic notation. Notice the atomic mass is on top and the atomic number is beneath. Both of these are representations of carbon-14. That means carbon, which has an atomic number of 6, has 6 protons, and how many neutrons? Well, if the atomic number is 6 and the atomic mass is 14, 14 minus 6 means we have 8 neutrons. There are 14 subatomic particles in the nucleus. 6 of them are protons, therefore the remaining 8 must be neutrons. Carbon-14, is a fairly common isotope of carbon, and it's in all living things. So nuclear decay occurs when a nucleus that is unstable emits a particle to become more stable. There are 3 ways in which we see nuclear decay. There are actually 4, but we're going to look at 3. First, alpha decay. Alpha decay occurs when you have a very large nucleus of an atom, and that nucleus emits a helium atom. That helium atom is a helium-4 atom. Therefore, it contains 2 protons and 2 neutrons. Here's our notation for it. You can see it has an atomic mass of 4 and an atomic number of 2. And here's an example of uranium-238 undergoing alpha decay. We start with our atomic notation for uranium with the atomic mass on top and the atomic number on bottom. And then we can write our alpha particle on the right helium with an atomic mass of 4 and an atomic number of 2, and then we simply subtract 92 protons in the uranium minus the 2 protons emitted as part of the alpha particle leaves us with 90 remaining protons. If we go to our periodic table and we look up the 90 as the atomic number, we see that if an atom has 90 protons, it is thorium. So we can go ahead and write in Th for thorium. Let's do the same thing for our overall mass. We started with 238 as our atomic mass in the uranium. We can now subtract the 4 that came out as part of that alpha particle, that helium there. So 238 minus 4 leaves us with 234 as the atomic mass of this thorium. So our resulting daughter atoms here are thorium 234 and helium 4, or an alpha particle. Alpha radiation can be dangerous if you eat it, but it generally is not dangerous to be exposed to because the radiation is stopped by a couple folded sheets of paper or clothing for the most part, your skin for the most part. Alpha radiation tends not to penetrate you. However, if you inhale it, or you eat it, or you drink it, then it enters your bloodstream and can cause all sorts of problems. So alpha radiation needs to be very carefully controlled. One of the places we see alpha radiation in our homes is in smoke detectors. Smoke detectors usually have a very small, most types of smoke detectors, not all, have a very small radioactive source that emits alpha radiation. Those particles, those alpha particles, are emitted by the radioactive source, cross over an open space, and then hit a detector. If smoke fills that space, the alpha particles cannot pass through the smoke. They get reflected by the smoke. And therefore, the detector does not receive the alpha radiation, and thus it says that there must be smoke, and thus there may be a fire. Beta decay occurs when there are too many neutrons in an atom compared to the number of protons. What is actually emitted is an electron. This comes from a neutron decaying into a proton. And in the process, the electron and a bit of antimatter called an antineutrino is emitted. What you need to know fundamentally is that the beta particle is an electron, and that when beta decay occurs, a neutron in the atom turns into a proton. So let's look at thorium-234 undergoing beta decay. We start with thorium. We look up that the atomic number is 90 on our periodic table, and we copy down that our atomic mass is 234 from the problem. And we can see that when we go through this beta decay process, that an electron is emitted. The electron has a notation of -1 as the atomic number and no atomic mass, right? Because electrons have no atomic mass. Why do we put -1 as the atomic number? Well, let's do our same subtraction. 90 minus -1 gives us 91. We have gained a proton, and the atomic mass has not changed. Beta decay can be dangerous. It has caused people to be sick and has caused people to die. There's a big example from Goiânia, Brazil, where someone broke into an abandoned hospital and took a piece of a beta emitter and ended up getting a lot of people sick, including his friend's wife and daughter. I think both his wife and daughter died. So it is very dangerous. That being said, it can be blocked with aluminum foil. So beta emitters are often stored in envelopes made of aluminum. Aluminum is flexible and easy to use, and in fact, our beta emitter at school is wrapped up in an aluminum foil envelope. Beta decay is used in archaeology. If you've heard of carbon dating, the way that works is carbon-14 exists in living beings, including us, and after those living things die, the carbon-14 slowly undergoes beta decay, decaying into nitrogen-14, because nitrogen has one less atomic number than carbon. By measuring the amount of carbon-14 compared to the amount of carbon-12 in a sample, scientists can determine within a certain range the date of death of those living things. And that's how we find out the age of fossilized plants, animals, dinosaurs, etc. Gamma rays are released from nuclei when they're undergoing other radioactive decay, fission, or fusion. They are the release of pure energy from the nucleus. Because they're pure energy, they have no mass. You could think of this sort of like Einstein's E equals mc squared. Because energy is equal to mass times the speed of light squared, because this has so much energy, all of that release is in the form of energy and not in the form of mass. So this doesn't change the makeup of the atom at all. It has the same atomic number, the same mass number. Gamma rays are dangerous. They pass through most types of shielding. They will pass right through house walls or car doors or clothing. And so to stop it, usually several inches of lead are put up, or concrete, maybe 6 to 18 inches of concrete, or even more commonly, water. Most nuclear reactors are submerged because gamma radiation does not go more than a couple feet through water. Gamma radiation tends to pass right through human beings. It goes right through your skin, right through your muscle, right through your bone, and keeps on going. That being said, if it just so happens to strike your DNA, it can cause a mutation in that DNA. The chances are fairly low, but if you look at stuff like the gamma knife, which is used to attack cancerous growths in the body, several gamma rays are focused on a single spot, which causes a large amount of gamma radiation at that one spot. And if they target that on tumors, that can be used to treat cancers. So let's do a couple practice questions. Number one, an element that undergoes beta decay will decay to another element with, that is right, B, a higher atomic number. Number two, the type of radiation that will penetrate farthest into a material is pure energy or gamma rays. Which radiation has a negative charge associated with it? This would be one that is an electron. Thus, it's a beta particle. Number four, an element decays multiple times, emitting an alpha particle and a beta particle. Its total atomic number will, well, the alpha particle will decrease its atomic number by 2, and the beta particle will increase it by 1, meaning the total is -2 plus 1 equals -1. It decreases by 1. Number 5, beta particles are stopped by aluminum. Number 6, if the number of protons equals the number of neutrons in an atom, the atom is stable. This works for smaller atoms. Number 7, the nucleus of an atom consists of protons and neutrons. Protons and neutrons, which combine to make nucleons, right? D. If you said C and D, that would be fine. Number 8, the force that holds the nucleus together is the strong nuclear force, or C. Number 9, when thorium ejects a beta particle, the nucleus left behind has 91 protons, right? We add 1 proton when beta emission occurs. Number 10, an alpha particle consists of, remember, it's a helium atom. So it has 2 protons and 2 neutrons. Number 11, the number of protons in the nucleus of an atom describes both, it defines the element and it is the element's atomic number, right? So that is both A and B. The atomic mass number of an atom refers to the number of protons and neutrons. So that is E. Number 13, carbon-12 and carbon-14s are both carbon, but they are different isotopes of carbon. Remember, an isotope has different numbers of neutrons. Number 14, which of the following is not emitted in radioactive decay? That would be A, neutrons.